Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, May 27th, 2022. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a warm and pollen-whipped spring evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I am grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry science and education associates, far-flung friends, family, and other curious folk. Thank you for participating. This evening, we have the unique privilege of hosting Kalina Nedkova, who will talk on how galaxies grow. Originally from Sofia, Bulgaria, Kalina is currently a graduate student at Tufts University, where she studies galaxy structure. Her main research goals are to explore and understand how galaxies have changed since the early universe. To accomplish this, Kalina uses data from the Hubble Space Telescope, but she's very excited to start her postdoc in September at Johns Hopkins University, where she will analyze data from the NIRIS instrument on the James Webb Space Telescope. I don't know how to pronounce NIRIS. In her talk, Kalina will discuss some of the ways in which the two main types of galaxies, star-forming and quiescent, have evolved over the last 10 billion years, and will touch on some of the physical processes that are likely responsible for this evolution. Of course, with the recent launch of the James Webb Space Telescope, as well as the exciting prospects with Euclid and the Roman telescope, we will soon have a much better and more complete picture of galaxy evolution. So without further ado, let's get to it. The Zoom platform is all yours, Kalina.
Well, thank you so much. It is a great pleasure to be here, and thank you to all of you who are here sharing your time with me on the Friday before Memorial Day. I really appreciate you being here. So let me share my screen and get going. Yes, so today I will talk about how galaxies grow. But before I do this, I think we need to together answer a more fundamental question, which is, do galaxies grow at all? So based on my first title, maybe you have some kind of a guess as to what the answer to this question is. But let me try to convince you that galaxies have indeed changed since the early universe. So to do this, I think one of the most powerful ways to see galaxy changes with time is to look at galaxies at different epochs of the universe. And we can do this because light only travels so fast. And so if we observe a galaxy that is very far away, it's going to take light emitted by this galaxy a long time to reach us. And so when we observe this faraway galaxy, we are seeing it as it was billions of years ago. In comparison, if we take a galaxy that's nearby, the light that is emitted by this galaxy will take less time to reach us. And so we are observing it as it was more recently. And so in this way, we can begin to look at different slices of the universe and look at the kinds of galaxies that live in there. So this is what I'm showing you here. On the x-axis here is a measure of time since the Big Bang. And so the Big Bang happened roughly 13.8 billion years ago, and the present day is shown here at 0. And I will also want to say a few words about this value here called redshift, because it will come up again later in my talk. Redshift is basically a measure for look back time. So essentially what is on this other axis here. And a redshift of 0 means the local universe nearby. And A redshift of 8, for example, already corresponds to 13 billion years ago. And so I will be talking about a redshift of 2. So just to give you a sense, a redshift of 2 is about 10 billion years ago. But the main point of the slide here is to show you that galaxies really are very different today than they were in the past. And so here I'm excited to share with you a little bit of exciting news. We have a newly identified candidate for the furthest away galaxy ever observed. It is not confirmed yet, but it was just announced in April, so it's very exciting. And currently the galaxy that, the furthest away galaxy that is confirmed is at about a redshift of 11, which is about 13.4 billion years ago. So this is to say that galaxies really started forming within the first few 100 million years after the Big Bang. And since then, they have been changing a lot. So here you can see that these galaxies are really clumpy. They look really irregular. And when you look at galaxies in the present day, they really have this nicely defined structure. And they might look like what you might imagine our Milky Way to look like. And so you're already beginning to see that galaxies are changing with time. But we can also look at this from simulations. And so, of course, our lifespans are too short to observe a galaxy throughout its life. And so galaxies really change on very long timescales. So if you want to follow one galaxy and see how it evolves, we really need to turn to simulations. So this is what I'm showing you here. Let me first say a few words about the numbers that you're seeing up here. So the first value, this is again the redshift. It's going to go from high redshift, which is the early universe, to low redshift, which is the local universe. And here is the measure of stellar mass. So this is the mass of the stars that live in these galaxies. You have the star formation rate. This is just the rate at which galaxies are forming stars. And it strongly depends on the amount of gas that you have. So galaxies need gas in order to form stars. And so in this right-hand side, you see what the gas is doing, and areas that look more orange, this means that there is a higher density of gas in these places. And so these will be the sites where stars are actively being formed. And you will see how this value changes as this gas evolves. And finally, here is a value that is called the specific star formation rate. It is not particularly important for us now, but I'll come back to it later on in my talk. And it is just the star formation rate divided by the stellar mass. Okay, so I will now play this for you because I think I've described everything. So again, just to remind you, here we're seeing the stars. So this is what we might observe with a telescope. And here is what we would see if we could just see the gas and what's happening with the gas. And so as time evolves, we see that these bigger galaxies are eating up the smaller ones. And you can see, oh, now you're going to see another view because this is a 3D simulation projected onto a 2D plane. And you see these galaxies really begin to interact. The gas is doing all kinds of interesting things. You see these events where the gas sort of gets blown away. These are processes that cause the star formation rate to decrease. And they're just, for example, supernova stars that are so powerful that they eject a lot of the gas. And so here you're starting to see a very nice looking galaxy in the center. Maybe you've noticed that it has significantly grown in mass. It started at something like 10 to the 10 solar masses, and it is now almost at 10 to the 12. If I pause this for just, oops, sorry, let me go back to where we were. Nope. Always tough with videos. Okay, let me pause this here. So if we look at this, this little galaxy, you can see has an incredible amount of gas. But this one, this big galaxy that has a lot of stars, which we can see because it's very large and it's bright in this plot, but not in here. This shows us that this galaxy really has very little gas, which means that it is really forming very few stars. So this is why the star formation rate for this object is so low, is because it doesn't have very much gas in it anymore. Whereas other objects like this one really are very gas rich, and these would be forming stars. So let me just wrap this up, and we can enjoy the remaining parts of the video together. And so yes, we have this final galaxy at redshift 0, and it has certainly changed a lot from what we started with. And this simulation is done by the illustrious team, which is comprised of all of these astronomy superstars listed here. And so I hope that now you're fully convinced that the answer to this question is that yes, galaxies absolutely do change with cosmic time. And they're also growing, as we saw, they're growing in mass, and they also appear to be growing in size because they started out small and now they're getting big. Okay, so now we can talk about how this happens. So in my talk today, I will give you a little bit of an introduction. Since I am sharing some of the work that I've done, I'm going to talk about how my collaborators and I have modeled the galaxies in our sample. Then I will talk about the mass and size growth that we measure. And finally, I'll say a few words, if I have time at the end, about galaxy components. And this is because galaxies are often treated as single objects, as one component systems. But if you look at some of these galaxies, for example, this one, you see that there's a lot of interesting substructure in there, and the different properties of these substructures indicate that they have different formation histories. So treating galaxies as one component is oftentimes an oversimplification. But okay, let's dive into the introduction. So I'd like to start with a brief story of the Hubble Deep Field, just to give you a little bit of an appreciation of where we were a few decades ago and where we are now. And I'm sure that some of you may have can tell this story perhaps better than I can, but we can certainly talk about that afterwards. So the Hubble Deep Field was selected. It is this little area that is outlined in yellow. And it was selected because it appeared to be relatively devoid of any objects. So there doesn't seem to be very many stars or galaxies in here, right? And so astronomers pointed the Hubble Space Telescope at this field. And in 1995, the first image of the Hubble Deep Field was released. And this is what it was. So we started with this little seemingly empty patch. And after observing it for many hours with the Hubble Space Telescope, we really see that there are so many galaxies in here that all have all kinds of different properties and different characteristics. More recently, the Hubble Ultra Deep Field was imaged. And now the Hubble Space Telescope has the advanced camera for surveys, which was installed during a servicing mission in 2002. So we have slightly better instruments aboard the Hubble Space Telescope. But so here is an image from 2004. And so again, you can kind of see that there is really no shortage of galaxies, and they come in all different kinds of properties. Some are really blue, others are really red. They come in a variety of different shapes, sizes, and colors. And so just to give you a sense of what's coming in the future, so here is the Hubble Ultra Deep Field, which I just showed you. And here in orange is the Nancy Grace Roman Telescope Field of View. It has 18 different detectors, and they will be able to image with the same kinds of properties and the same amount of detail as the Hubble Ultra Deep Field, but you can see that it covers an amazingly large area of the sky. So it's really, I think it's going to be mind-blowing. You know, we can't wait for the Nancy Grace Roman Telescope, which is set to launch in May of 2027. So again, I will point out again that you know, in the Hubble Ultra Deep Field, we see a variety of different galaxies. Despite this variety, I'm going to argue to you today that most galaxies can be classified into one of two types. There are, of course, exceptions to these, but for the most part, this is true. So either a galaxy is disk-like, so think like a frisbee. It is star-forming, meaning that it is forming new stars, which tend to be blue because they are very hot. And therefore, the whole galaxy appears blue due to its young stellar population. And it's clumpy. What I mean by this is that if I start from the center of this galaxy and I move out radially, there are parts of this galaxy that are dimmer and parts that are brighter. So the profile is really not smooth, it's clumpy. On the other hand, you can be a spheroidal galaxy. So like a basketball or any kind of sphere. These are generally quiescent, meaning that they are not forming stars. These are also historically called early type galaxies. They appear red because they are no longer forming stars, and the young stars tend to have very short lifespans compared to the old stars. So the very hot young stars have died off, and all that's remaining is the old stellar population, which appears red because it is not as hot, so it is a little cooler, and this gives rise to the red color that we observe. And again, if I play the same game where I start at the center and I move out radially, the profile looks really smooth. Okay, so also these blue galaxies tend to be larger but less massive, whereas these red spheroidal quiescent galaxies tend to be smaller but more massive. So let me tell you where these types of arguments come from, specifically for the size and the mass. So here is a work from Arjen van der Wel from 2014. I think that this is really kind of the standard in the field at the moment. And so what's shown here is the radius of the galaxy on the y-axis in kiloparsecs. And on the x-axis is the stellar mass, so the amount of mass in stars. And so on this plane, if we separate the galaxies into our two types, the blue and the red, here, so the blue is star forming and the red is quiescent, then we see that they occupy relatively different areas of this plane. And so if I pick a size, let's say I pick 5 kiloparsecs and I move across mass, I see that the quiescent galaxies, these red points, are more massive than the blue points. So that's where the first argument comes from, that the star-forming galaxies are less massive than the quiescent ones. And likewise, if I pick a constant stellar mass and I move across size, again, I see that the quiescent ones are smaller than the blue ones. And so just to put this in writing, the quiescent galaxies are on average smaller than the star-forming ones, and they're also more massive. The other thing to notice on this plane, which I haven't talked about much, is that these different panels show you different redshifts. So I'll remind you again, a redshift of 0 or a low redshift is closer to us, and a high redshift is in the early universe. And so what we see is that if we fit lines to these trends at the lowest redshift bin, and then we also overplot these in the subsequent redshift bins, what we see is that there's a shift, a change in the normalization of these best fit lines. So what this indicates to us is that on average, higher redshift galaxies were smaller because the intercept of these lines is getting smaller. So these both star-forming and quiescent galaxies were smaller in the early universe than they are today. And I think you also got a sense of that from both the video and the picture of the universe that I showed at the very beginning. But here is a plot that shows this, I think, in a more scientific way. So I will be talking about mass-size relations for some time. So, if you have any confusions at all, please let me know, and I'll be happy to clear that out. Okay, so what does this mean? Why do we observe quiescent galaxies in one part of this plane and blue star-forming galaxies in another region? Well, luckily, this has already been answered. So if I think about the mass size plane, then the star-forming galaxies are going to be dominated, their growth is going to be dominated by the formation of new stars. And so they're going to grow in both mass and size. So they're going to evolve along this green line. At some point, they're going to hit a threshold, which causes them to quench. And once they quench and stop forming stars, their growth is now going to be dominated by mergers, specifically dry minor mergers. So a dry merger basically means that the galaxies that are merging are gas poor, and a minor merger just means that the ratio of the two masses, one galaxy is much more massive than the other one. And so if you have this dry minor merger that comes in, it's going to disrupt the orbits of all your stars. And so the effect that it's going to have is it's going to puff out the galaxy, and it's going to make it grow in size much more than it does in mass. And so a typical galaxy in its evolution might undergo some kind of path like this. Of course, you saw earlier that the sizes of the galaxies change with redshift. And so the place where these galaxies start off is going to depend on the redshift. So galaxies in the distant universe far away are going to start off down here, whereas galaxies closer to today are going to evolve from a higher mass, a higher size. And also another thing that changes here is the threshold also changes with redshift, but it's not particularly important for today unless you're particularly curious. Okay, so it seems like we have a lot of data and we have a nice explanation for why we observe the things that we observe. So why am I here talking to you today about mass-size relations? Or in other words, what questions still need to be answered. So we could talk about the effects of environment. It is known that galaxies that live, for example, in cluster environments will evolve through different processes than galaxies that are isolated. We could also extend this to higher redshift than they have here. So how do galaxies in the very, very, very early universe look like on this plane? Or we could extend this to lower stellar mass galaxies. So what happens below 10 to the 9 stellar masses? So I've highlighted this last point because it is the point that I'm going to talk about for the remainder of my talk. Okay, so what do we need to extend this relation to include lower stellar mass galaxies? Well, we need an excellent data set. And so you might recognize this from the title slide. These are images of the Hubble frontier fields. They are 6 clusters, which are shown here on the top. These are very dense environments that are imaged in parallel with 6 blank, not so blank, parallel fields. So this is fantastic because it allows us to observe galaxies that are very faint. And faint galaxies usually also mean that they are less massive. We have combined this data set with the CANDLES survey, which is again using the Hubble Space Telescope, but it is not quite as deep. So we're observing, we're not able to observe those very faint galaxies in CANDLES, but CANDLES covers a very large area. So we've kind of combined these to get the best of both worlds, both deep data and also data that covers a large area. We need to get the masses of these galaxies. There are several ways to do that, which are well established in the field, and so I won't discuss them too much, but all of them come with their own assumptions and their own problems. But the thing that I will talk a lot about is how we get the sizes of these galaxies. So we do this with light profile fitting. So if you imagine a perfectly spherical object that is emitting light, then what I will be calling the size is the radius at which half of the total light is emitted. And so then you might ask, well, what if you don't have a perfectly spherical object, but you have an ellipsoid? How do you measure the radius? Well, we're going to use the semi-major axis. And so again, we will measure the semi-major axis at which half of the total light is emitted. And finally, we need the distance to the object. For our sample, we have, so we need to measure the redshift, right? So for our sample, we have both, photometric, spectroscopic, and GRISM redshifts. Especially for the spectroscopic and GRISM redshifts, these are relatively reliable. Okay, so let me talk a little bit more about how we get the size of the object and how we do this light profile fitting. Oh yes, and I should say, before I forget, a lot of times people ask me, if you have this ellipse and you're trying to measure the semi-major axis, this also depends on the orientation of the galaxy with respect to you, right? And so I will say that very smart people have developed ways to measure the radius of these galaxies that take into account the axis ratio and the position angle. So all of these kind of details are already taken into account for me. Okay, so now I want to say a few words about modeling galaxies. So like I said, we use the Hubble frontier fields, which have imaging in a number of different bands. And so some of them, not all of them, are listed here. Basically, what I want to point out here is that we want to take advantage of all of these different filters all of the images in these different filters and use them to model our galaxies because each one contains really important information. And a lot of times when people model galaxies, they only use one filter in which they model the galaxy, but we have done something better. We have done multi-wavelength fitting. So here I'm showing you 3 example galaxies. For each galaxy, I'm showing you the image in the band. So in 7 different bands here, starting from the F435, which is at a relatively blue, a blue wavelength, and going all the way to the F160, which is at 1.6 microns, so into the mid-IR. And so here is the image in each one of those bands. Here is the model. And here in the last column, I'm showing you the residual, which is just the difference between the image and the model. And so these are not selected to have particularly clean residuals or particularly nice models. They're kind of selected to have different properties. And just to show you that the modeling does work for a variety of different galaxies. And I said that fitting in multi-wavelength with a multi-wavelength approach is great, and it allows us to use all of the information in all of our bands simultaneously. But you can see that galaxies really look different in different bands. And so how do we connect the properties of the galaxy in the blue bands compared to the redder bands? So what we do is we fit some kind of polynomials through the observed bands. So here I'm showing you 9 different bands, so not the same ones that we used for the Hubble frontier fields, but 9 different bands. And here is the magnitude or the brightness of a simulated galaxy. So we know its true magnitude, we know its true brightness, but we're now going to measure its brightness using each individual band by itself, so each individual filter by itself, and compare it to the fit with the multi-wavelength approach. And so the X's here, these are the truth. Since it is a simulated galaxy, we know the true magnitude of it. And you can see that for noisy bands, especially, if one of these bands is made particularly noisy, then we can still get a much better estimate of the brightness using this multi-wavelength approach. And so we not only fit the brightness in this way, we also fit the effective radius, which is again what I'm calling the size. And so you can see that for very noisy bands, this does a much better job of fitting the parameters in a meaningful way. And this is also true for some other fitting parameters that we can estimate. So this is all to say that using the multi-wavelength approach really allows us to better constrain the physical parameters of the galaxy. And this multi-wavelength fitting is done with a code that is called GalFit-M, which is written by Boris Heusler, who is a wonderful astronomer and extremely knowledgeable. So if you want to know about multi-wavelength fitting, he's a wonderful person to talk to. Okay, so now since we have these excellent models and we have these excellent estimations of galaxy size, now I want to show you the mass and size growth. So we have extended the mass size plane to include lower stellar mass galaxies, which was our goal. So the first step that we need to take is to separate galaxies into star forming and quiescent. And so one way to do this is to, so the fitting doesn't tell us whether things are star forming or blue or spirals. It just measures the size. And so we ourselves have to classify the galaxies. So here is a picture of what is known as the Hubble tuning fork. For those of you who are musicians, you might see why. And basically you have ellipticals on one side, so quiescent spheroidal galaxies on one side, and star-forming disk-like galaxies on the other side. And so we could go through all of our galaxies and classify them visually, but we have a lot. So it's not really feasible to do this classification by eye. And I think as more of these very exciting instruments are coming online, we're really going to have a problem with handling very large amounts of data. So we really need our methods and our techniques to keep up with the fantastic amount of information that future telescopes will obtain. So instead of classifying things visually, instead we will classify galaxies based on their colors. So for astronomers, colors are ratios of fluxes in different bands. So here, this is what astronomers will call a color diagram. Basically what it is on the y-axis, you have the ratio of flux in the U and the V band. And on the x-axis, you have the ratio of flux in the V and J bands. And so what this does is that it helps you separate galaxies that are red and galaxies that are dusty. So on here, you will separate galaxies that have red colors because they have old stellar populations, because they're no longer forming stars. And on the bottom, you will have galaxies that are forming stars and therefore appear blue. And the other color is used to distinguish between dusty and non-dusty galaxies. This is because if you have a star-forming galaxy and it's very dusty, it will absorb light from the blue wavelengths and re-emit them in the red. And so there's this kind of degeneracy that we need to take care of. And so this color diagram helps us do this. And also here is our old friend, the specific star formation rate, which I said just a few words about at the beginning when I showed the video. But this is also used as a way to distinguish star forming and quiescent galaxies. And you can see that this diagram is relatively consistent with the specific star formation rate, in that galaxies that are color-coded blue lie outside this little wedge, and galaxies that are color-coded red are within it. So the galaxies that are within this region will be quiescent. And so this is just to point out that there's a number of ways to select quiescence. So here is what the mass size relation looks like if we use the UVJ diagram, which is this method. So just the ratio of flux in two different bands. So you can see now that before we were going to about 10 to the 9 stellar masses in the Arjen van der Waal paper from 2014. And now we have extended this to 10 to the 7. And so we can also select these galaxies based on the shape of their profile. This method is somewhat prone to problems, so I'm not going to spend a whole lot of time here, just wanted to show it very quickly. And then we can use the specific star formation rate, which seemed to correlate very well with the color diagram. And so if I put all of these together, all of these selection techniques are independent. So they're independently derived. And you can see that the trends exist in all of them. So this suggests that the trends that we are seeing are not a product of the way that we are selecting our galaxies, but are in fact really present in our data. And the thing that I think is most interesting here is that there's this flattening in the quiescent galaxies. So they start out with this very steep relation, and then they flatten at lower stellar masses. So let me show you now this plot where I have plotted all of the galaxies in black, and then the things that are in blue and red just show you the best fit trends. And so at the high mass end, we see somewhat similar results to what was observed before, namely that the growth of quiescent galaxies is very steep. So they are growing a lot in size, but not very much in mass. And again, we believe that this is a result of dry minor mergers, and the star-forming galaxies are growing as a result of star formation. But now there appears to be this other region where the quiescent galaxies, the low mass quiescent galaxies, have this flattening. So how can we explain this? So if you notice here, there are these lines of constant surface density. These basically mean that if the relation that I'm looking at is steeper than these constant lines, then most of the mass of the galaxy is being built up in the outskirt. If these relations in blue and red are shallower than these lines, then most of the mass is being built up inside the one effective radius. And so what this tells us is that there is no way that these low mass quiescent galaxies are evolving through dry minor mergers. There must be some other physical mechanism that is driving this galaxy evolution. And also I want to point out that this flattening can be observed for sure up to a redshift of 1 and possibly out to a redshift of 2. But below a certain mass and these higher redshift bins, we are incomplete. And so we really need those better instruments like the James Webb Space Telescope to fill in the space in the future. Okay, I think I'm going to skip this part. And just I want to say that we have extended the mass size relation to significantly lower masses across a redshift of 0.2 to 2. And we observed this interesting flattening in the relation, in the mass size relation for the quiescent galaxies that hasn't been seen before. Okay, so now I want to say a few words about galaxy components. And just to show you this. So if you have a star-forming galaxy, so this would be only a disk. And if you have a purely quenched galaxy, this would be what we call mostly a bulge. But if you look at a galaxy like our Milky Way, you can see that it really has what looks like this spheroidal part in the center and this disky part in the outskirts. And so really these galaxies can be decomposed into a central bulge with a surrounding disk. And so here I have one of our old friends from a few slides ago that we looked at. And here I just want to show you that we can do the same kind of multi-wavelength fitting to obtain the disk and the bulge component in multiple bands. And then we can estimate the sizes of the disks and the sizes of the bulges to derive the mass size relations of not galaxies as a whole, but galaxy components. And so this is work that is still ongoing, but I would be happy to share it with you in the near future. And I just want to end by saying that this is a very exciting time for astronomers. This has been a point that I've been trying to make throughout my whole talk. But it's really, I think we're going to really revolutionize our field in the near future, thanks to the James Webb, the Nancy Grace Roman Telescope, and Euclid. So with that, I will just pop up my summary and say thank you so much for listening. It's been a pleasure being here and meeting all of you. Thank you.
Thank you.
Yeah. Thank you so much. We have time for questions if you're willing to field them.
Of
I have a
course,
question.
please.
So you're describing finding patterns in galaxies, basically, and their growth.
Right.
You haven't talked about the variance around the mean.
Oh,
Is there a lot of variance around the categories you come up with, or is it pretty tightly fit?
yeah, that's a great question. So I can talk about variance in, I think, almost every step that I take. So in, let's see, if I go back. So in the selection of star forming and quiescent, so we use these two, or rather three different methods, basically to show that the methods are consistent with each other. And so a galaxy that is selected as quiescent, it doesn't, let me see how I can phrase this in a clever way. It doesn't matter if a specific galaxy is labeled as quiescent or star forming by these different trends or by these different selections. What matters is that the trend that we're seeing, the overall trend that we're seeing, is consistent between selection methods. So maybe a galaxy here or there or is classified differently based on the selection, but the overall trend that we're seeing is not affected. So the overall trend remains consistent regardless of the selection that we use. And so therefore we feel very confident in saying that there is this flattening in the relation for the quiescent galaxies because it is not dependent on the way that we classify them. Now, I can also talk about the variance within or in the fits, right? So that's what these kind of shaded regions are. So these indicate, so here is the best fit line that is derived with a Bayesian approach. And here is the amount of scatter that you might expect if your star forming galaxy in this plane, you might be within the shaded region.
So the shaded region is how many, that's what I want, standard deviations away?
Yeah, exactly. The shaded region is exactly 1 standard deviation.
Okay, thank you.
Yeah, thank you for the great question.
The error bars.
Are there error bars? Yeah. Yeah, so there are error bars on the sizes that we derive here. The sizes and on the stellar mass, in fact. The error bars on these points are taken into account when these lines are fit. So if a certain object has very large error bars, it will not influence the fit as much as an object with small error bars.
It looks like the error bars increase with the redshift.
In the fit, indeed.
Okay.
So here I have, in fact, so the error bars do increase. You can see that there's significantly more scatter around the lines. And then another problem is that at a certain point, we're just not observing enough galaxies to fit trend lines to, right? So we don't want to fit 5 galaxies in here and say that this is representative of a whole galaxy population. Instead, we just want to show that we're confident in this trend line until a stellar mass of 9.2. And then below that, we have extrapolated the fits to the data. But indeed, also the error bars on the galaxies themselves grow with redshift because, of course, galaxies that are farther away
Distance, yeah.
appear dimmer and they are harder to measure.
Okay, that part I didn't catch.
Yes.
You mentioned that the spheroids were smaller than the spirals. I thought the biggest galaxies were spherical.
Yeah, no, that's an excellent question. So I'm talking about on average.
Okay.
So yes, there are. So if I point back to what I think is the standard in the field, there are galaxies that are very large and very massive that are also spheroidal. But as a whole, the population doesn't seem to be doing that. And so, yes, I'm talking about trends, overall trends in galaxies, rather than finding the extremes, which is also a very exciting and interesting thing to do.
What is the barred spirals? I mean, what's a bar? How does that come about?
Great question. Yes, bars I would say are another component to the galaxies. So I talked about needing to decompose the galaxies into components, and the bars are a great reason to need to do that because as you can see in Hubble's tuning fork classification, the barred galaxies really look different than the non-barred galaxies. At high redshift, at the redshifts that I'm talking about, it's extremely difficult to distinguish a bar from a regular bulge. And so for us, I think that a bar would just be modeled as a bulge, even though a bar and a bulge are don't necessarily have the same properties. But at high redshift, everything becomes a little fuzzy.
Wow. This doesn't take into account dark matter or dark energy parts of the equation at all. This is what you're seeing, that's it.
Yeah, this is purely observational. Yep.
Wow.
So we have some good questions in the chat from Rick Upton. What is the driver behind the merger of quiescent galaxies?
Excellent.
Is it black holes or dark matter or what?
Excellent question. I will come back here and play this again for you. So yes, it's because galaxies live in dark matter halos, and the dark matter halos interact gravitationally, so they will be, attracted to each other, and galaxies with smaller dark matter halos will be pulled into the very massive dark matter halo.
And this is kind of ancillary to that question from Paul McGeary. When Andromeda and the Milky Way collide in 4 to 5 billion years, what shape and mass will the resultant supergalaxy have?
Yeah, brilliant question. I have to admit, I'm not very familiar with things in our local universe, but let me try to answer this nonetheless. I'm not sure when they will collide. So this would be a major merger because the Andromeda Galaxy and our Milky Way. I believe the Andromeda Galaxy is more massive, but they're comparable. So this would be a major merger. But I hear a lot of times people are very worried about our sun, colliding with other suns and or other stars, and what's going to happen. And the truth is that these galaxies are really rather diffuse. So I think that we have they're mostly just going to pass through each other. What will happen in billions of years after they collide is they will exchange their gas. There will be this burst of star formation, which will then quickly quench, and you will be left with something that looks like a spheroid, like a quenched red spheroidal galaxy.
Red and dead.
And this question relates as well from Eleanor Harris. Has the reason galaxies quench, in that they stop forming stars, has the reason been agreed upon? Is the existence of a supermassive black hole playing a big part?
Yeah, that's a very nice question. Thank you. There can be a number of reasons why galaxies quench. They can indeed quench as a result of the supermassive black holes in their centers, especially if they're active, which is what we call AGN, so active galactic nuclei. These blow away all of the gas, they heat it up so that it cannot form stars in a very efficient way. And so once you have an AGN, it's likely that the galaxy will quench. There are other ways that you can quench galaxies. You can have something like Ram pressure stripping, where if you are a galaxy that is coming into a cluster environment, it's like, I've heard it described as riding your bike on a hot day, and you feel this kind of, if you pass, you feel this kind of like wind pulling everything away from you. That is what galaxies undergo in Ram pressure stripping, is all of their gas just gets pulled away by other objects. So really, I mean, what I'm trying to say is that there can be so many different ways that you quench a galaxy. You can have starvation, where the galaxy loses all of its gas due to another more massive galaxy pulling that gas away. So it really depends, I want to say. So it depends on the environment, it depends on the mass of the galaxy. So it's hard to say. There's no one clear path to quenching a galaxy. There can be many.
I think this is an easy question for you, from Yves and Michelle Simon. It looked like in your picture of the Milky Way that the center is red and the spiral arms are blue. Can we conclude that there are new stars forming in the spiral arms and the center is quiescent?
Brilliant question. Yes, we can. The centers tend to have the same kind of properties that quenched galaxies have, and the outskirts tend to be, because they look like blue star-forming galaxies, they do in fact tend to be star-forming. Yes, yeah, exactly.
So this is the last chat question from Michael Eisner. Hello, Michael. He's a cousin of mine. Why do they all rotate the same direction? So you might want to verify whether that's true first.
I think so. In here, is this the question?
The question is really based on why all galaxies rotate, or to confirm that all galaxies rotate in the same direction. Stars, solar systems generally rotate in a certain direction.
Oh, within the same galaxy, yes.
Well, within the same galaxy, and galaxies rotational as well, right? So they all rotate more or less the same way relative to Earth.
Is there a clockwise, counterclockwise preference?
That is something I do not know about, but would love to learn about because that would be very curious. Yes, I know that when galaxies are first formed, they have angular momentum, which gives rise to the beautiful disks, the thin disks that we see. But in which direction they rotate, I think.
Wouldn't that depend on whether you're galactic north or galactic south, which side you're standing on?
Well, it's northern hemisphere, southern hemisphere. You're in Australia or the Americas,
Is there a top and a bottom to a galaxy, really?
or just viewing it.
I'm not sure.
There's a question to answer then.
Yeah.
A new one.
So I think unless others have more questions, I have a question that you will be able to probably resolve very quickly.
Okay.
Back with the Hubble Deep Field and then the Hubble Ultra Deep Field, there was a lot written about galaxies, what I like to call little red turds at the edge of infinity, that had spindle-like shapes or wormy shapes, and not disks or spheroids. What has happened to that interpretation?
Okay, I'm not terribly familiar. I think possibly we call those red nuggets now,
Nuggets,
but I'm
okay.
not sure. Yeah, I'm not sure. Yeah, that is again something I'm not familiar with. But like I said, I mean, separating galaxies is something that is generally true, but of course you will always have unique and interesting galaxies that don't fit into those two broad classifications. So, it's very likely that we have something very interesting in our sample here that we're just kind of smoothing over, and we're classifying as one of these two, but really it could be a very interesting object, but
Okay, good.
not
I
familiar.
look forward to further resolution then.
Yes, me too.
So any other questions then?
Go
I
ahead,
had
just
one,
ask for a quick, I'm sorry, go ahead.
No, I wanted a clarification on your clusters comment.
Yeah.
You talked about the fact that galaxies in cluster formations that have proximity to each other have a different dynamic than ones that are alone. Why would that possibly be, given the vast distances between them and likely zero influence between them?
Yeah, great. So because clusters are so dense, actually all of the gas around the cluster is hotter than the intercluster medium is hotter than, say, a galaxy that's just living by itself. And so because it is hot, that means that a galaxy that is moving into the cluster will experience this ram pressure stripping that I mentioned previously. So this doesn't happen outside of the cluster. So there are processes like ram pressure stripping that are specific to the cluster. And there are vast distances between these galaxies, you're absolutely right. But they're all settling into the same gravitational potential well. So, they're all moving into the center. As you saw in the video, these galaxies all move into the center of, right, they all end up in the center because they're all kind of moving into the potential well. So they may be very far apart, but they will eventually interact and eventually merge. So that's all I meant by that processes that happen in these dense clusters are different than a galaxy evolving on its own, isolated from others.
These are on filaments and moving towards nodes.
Yes, they are. Yes.
Okay.
Yes.
Beauty.
It's an interesting, the biggest things in space are the blanks, the empties, the voids. Where
Yes.
the dirt, where the edges. Wow.
So
Yeah.
Michael,
What part of the country are you broadcasting from? Just out of curiosity.
Oh, so I'm a graduate student at Tufts. So I'm in the Boston area.
Wow. Okay.
Yeah, relatively nearby.
Couldn't tell you weren't Southern accent or anything like that. So I bet it's New England. All right.
yeah,
Hope you visit us sometime.
yeah. I would love that. That would be fantastic.
Michael, make it happen.
I have a really quick clarification to ask for, and it'll take you one word to answer.
Okay.
That'll be new.
On average, did I hear you correctly when you said, when I think you said that in general, ellipticals are not giant and larger than spirals?
Yeah, we did this already.
Yeah,
Yeah.
I want it to be clear. We're talking about, because the word giant doesn't get appended to spiral all that often, but it gets
Yeah.
appended to elliptical
Yeah.
all the time. And I thought ellipticals ate spirals.
Yes. Yes.
Well, spirals turn into ellipticals.
Yes. Yes. So yes, you did hear me correctly. I am saying that if I look at a given mass, quiescent spheroid red galaxies are on average smaller than the blue star-forming galaxies. I think what we're getting into here is talking about the very most massive galaxies that we observe in our universe, which I think are more massive than certainly are more massive than 10 to the 11, would probably be about 10 to the 12 perhaps. So those would really be kind of, well, actually, maybe I can jump here, because what I observed is that really the most massive and the most, let's say, large galaxies are indeed quiescent. So this is what I observed, but it's just that star-forming galaxies don't get this massive. I guess is one way to look at it. And you know, with increasing at higher redshift bins, with increasing redshift, it's harder to make robust measurements of mass and size. So just looking at this lowest redshift one, indeed, the most massive and the largest galaxies appear to be quiescent, but as a trend, as a whole, they appear, you know, the quiescent ones are smaller than the star-forming ones.
Okay.
But you're absolutely right.
I'm going to have to nurse my cognitive dissonance here for a couple of weeks.
yes, this is a new result, kind of exciting. And I wish you the best of luck as you start getting more sensitive data from these other telescopes and more wide-ranging fields. And as you move on to a postdoc at Johns Hopkins.
Yes, thank you so much. It was such a pleasure to talk to all of you. Thank you for all your questions.
All right,
Great presentation. Thank you very much.
Thank you.
thank you.
Thank you. Yeah, I have one more question, if you.
Please.
Okay.
Yes, please.
Yeah, it's a follow-up. If there are more stars forming in the spirals than in the center of galaxies, do we know why?
Yeah, that's a good question. Yeah, so stars are, so if I have this kind of galaxy that has the disk and the spheroidal part, indeed, most of the stars will be forming in the center here, and the old stars will be in the center.
Mhm.
And it's escaping me at the moment why this happens, but it's a very simple reason. But I have to, yeah, I think I have to think about it for a minute.
They already formed a long time ago?
But yeah, these galaxies, yes, the centers formed, the stars in the center formed a long time ago, so they're older. And then the ones in the spiral arms are being formed now, yes.
Yes.
But why are they formed there and not in the center? Huh?
Yeah, yeah, I understand your question, and I think there's a very simple explanation, but it's just it's escaping me at the moment. And
Yeah, okay.
It's what's left. It's what
Um,
remains is the gas is in the disks, and so
yes, there we go. It's the gas. Yes, it's the gas. Thank you.
it's always the gas.
It's always the gas. Yeah. Yes, it's
Means.
because the outskirts are more gas rich, and so the center can no longer form new stars, and so as the stars get old, they will emit in these red
Mhm.
colors and the blue ones. But you can still see that there is some star formation going on in the center. There is still that underlying disk in there. You just basically have these two structures
Mhm.
on top of each other.
All right,
Yes.
that has been clarified.
Thank you. Yes. Oh, it's always the gas. How could I forget?
So I think I will call it quits here and stop the recording and wish you all well. I thank you so much.
Great presentation. Thank you for
Thank
the
you.
opportunity.
Thanks.
Have a great night.
You too. And
Right.
happy Memorial Day.